I'm going to tell you about work that we have done in the last semester at Berkeley with Or Satat and Aaron Broduch. And it's a work about attacking a protocol that's actually not done in this way. We're attacking a straw man, but it's so interesting that I'm going to tell you about it anyway. So the talk is an adaptive attack on Wiesner's money. And well, how we're going to do it, we're going to try to explode some quantum bombs or test them or so. And possibly this is going to be something that you will be able to teach in your intro quantum courses because it's so simple. So this is Or Satat. This is the place where we've debated and found this out. And this is what I'm going to tell you about. When we're buying stuff, I give you money. I give a bank or a shop money. I get something. I get produce. But maybe I would like to come with some play money and some fake money and get more of that stuff. But what I'll get from the bank, like, come on, what are you trying? Hey, take your play money back. Or sometimes like, you're here again, I'm not giving you anything back and I'll send you away. And maybe later they'll get even more angry and just send me to jail for this. So basically I'm going to try to do things to really discourage people from faking money. Okay? So this is what I will call strict testing. I'll come with good money, I'll get the good money back and a validation, yes, this was good money. Or when fake money comes, I'll get sent to jail. Or make it even worse, they'll kill me. Okay? So this is the strict testing. So first I'll tell you about quantum states that can be expensive, the money, and how I would want to test whether we can reuse them or possibly validate them. Second, I'll tell you about the bomb testing and how we can break this money with it. And finally, I'll give a generalized procedure, which we don't have in the paper yet, but it will be there hopefully soon, where we can do single copy tomography with a strict verifying tester, meaning if I have a box that can validate whether the money is good, I can find out anything about the money, anything I want. I can do tomography. And if I don't succeed in the test, you kill me, and I can still do this. Okay? So let's go to Wiesner's money and strict testing. Wiesner's money that came in the early 70s and was published 15 years later is just a description that I have a thing that has a serial number and then also has a hidden quantum state. That's a series of a sequence of zeros, ones, pluses, and minuses. And if the bank knows it's secret, it knows which basis to measure in, and it can definitely verify that the bill is good and valid. So this is also been seen in Yikai's talk as like a verify only or just a one-time memory, or as unforgeable subway tokens in a paper by Bennett, Brassard, Breitbart, and Wiesner in '83. And it's guaranteed safe when you use it once. So it really is just a token. So what's the probability that you can copy this when you have n of these qubits? Exponentially, it's either a half or 3/4 to the n. It's 3/4 to the n. All right, now what's the, could you make this better if we have 4 states here? Do you have an idea how to make it better?
If we have what?
4 states. Like,
it's identical.
Yeah, we can choose from 4 states. Can we make it better, like safer in some way? To choose from a different list of, states.
6 states.
6 states, yeah, that's 6 states, and that gets to 2/3. Now, there's a question of whether we can do this. What happens if, like, after time stuff deteriorates? Can we tolerate some noise? And it turns out that yes, and this is safe also, again, for one-time use with noise. It's been shown by Fernando Pastavsky and other people in 2011. And what they have shown that's nice about this protocol is also that you can only use classical communication, that you don't really need to send the qubits. The bank just asks, tell me, measure in these bases, give me the result. And then some of these bases are fake. And in the bases where it actually agrees, the bank checks whether everything is okay up to some fraction so they can tolerate noise. So this is nice. This is for one-time use. But I want to ask something different. Why is it just one-time use? Because if I can validate old bills, say either, okay, it's good money, I get it back, or if it's bad, the measurement result got bad, I get it back too. This is dangerous. Dangerous noted by Andy Lutomersky. Because, say, I take a qubit, I take it out, and then I guess a qubit. I send it to the bank, and the bank measures. And either it turns out what it's supposed to be, and I win, or it turns out wrong, and if I get the money back, I know which qubit is wrong, so I flip it, and I win again. Okay, so this simple attack breaks it. So you better not return bad money. Okay? So let's try this. How about not returning bad money, or making it even worse, killing you where you send me bad money? Okay? And is the forgery still worth it? And it turns out that yes, and we can do it efficiently if we do it adaptively. So we do it many rounds, sneakily, never dying, and copying. That's the idea. So let's do it. And we're going to do it by Elitzur-Weidmann's bomb tester adapted to our to what we want to do. So here's the bomb tester. Imagine that I have a system here, and this is a bomb. And whenever the system is flipped to a 1 and I measure it, it explodes. I'll add a probe system to it and rotate it by a tiny bit, by small delta. Now what happens here? When we're here, we get nothing happening to the system and a little bit of the system being flipped. Now I measure. When I measure the system, I die. But I'm here, I didn't die, which means that part of the wave function goes away, and what I'm getting here is just what I had before. And I recycle, and I do it n times. And after I do it n times, the final state of my probe is going to be the 0 state. And when I measure the 0 state, it says, be careful, there is a bomb. Okay? So remember this case. And in the case, when I have n rounds, and there's a little rotation by delta, then the probability of dying in every round is delta squared, and I do n rounds, so roughly the probability of dying is n times delta squared, or 1 over n. So if I choose a large n, I will not die. Next, if there is no bomb, so there's nothing here, well, what happens? The system always stays in this state, and the probe rotates, I recycle it, I rotates up to a 1, and the final state is a 1, and whenever I measure a 1, I know that everything is clear. So this is the bomb tester. Now, let's adapt it to cloning money. So, what I will do is the same thing. So here's a small rotation by delta, and I will use it on trying to figure out what happens with one of the qubits in here. 1 qubit from the money, from the bill. So it's either a 0 or a 1 or a plus or a minus. So if the qubit was a 0, what happens now? Well, just as before. It's cosine delta of nothing happening and sine delta, the qubit being flipped. And if the qubit is flipped, the bank detects it and kills me, which means this does not happen because I'm here still, and we're getting a plain 0 on the probe. And we recycle it n times, and that's it. The final state will be 0, and the probability of us dying in the process is again 1 over n. Good, now what happens if the qubit was a 1? The secret qubit. Very similar, because it's flipped. If this is a 1, it gets flipped. So it just, what changes here is a 0, 1, 1, but nothing changes on the probe. Okay? So a 0 or a 1, they both get flipped to an orthogonal state, so it's like a bomb. Now, what happens for a plus? What if the secret qubit was a plus? When there's a C naught here, what will happen? Nothing happens because this is a controlled x, and plus is a plus 1 eigenstate of that. So that means this stays as a plus on the bottom, and there's a delta, and I keep doing it, and I'll get 2 delta, 3 delta, and so on, up to a 1, because I do it n times, and I rotate it up. So the final state of the probe, if this qubit was a plus, is a 1. So I can already tell 1 away from 0 and 1. A plus away from 0 and 1. Now, the challenge, finally, this was the only hard thing to calculate. Now, what happens with minus? It's a phase flip, but it's not a global phase flip, because if this is a 0, that doesn't get a phase, and if it's a 1, it does. So when I have this, the minus will phase kick back here, only on this part. Oh, there should be a 1 here. So that means that the state here, when it was delta up and I was a little bit looking, then only this part got a minus, so I got rotated like under the axis, so it becomes a state minus delta. And when I take the state minus delta here, and I rotate it, it gets rotated back to 0. And if it's a 0, nothing happens here. And the 0 gets recycled here, and runs through, and I get a minus delta, and then I get back to 0, and I get plus delta minus delta 0, plus delta minus delta 0, and that's it. So in the case the special qubit was a minus, the probe will just cycle around 0. And when I measure it, I will measure a final state that is a 0. So when I look at all that, I have just figured out that it's 1 out of 4 states. So I can tell which, if it was a plus, I can tell it. So how can I identify a different state besides plus? What should I do? I can either rotate it initially, or I can just do, not instead of a C naught, I can do a control Z, say, or control minus naught or something. So I can identify all states as I want, and the probability for the procedure of failing is 1 over n. So if I choose a large n, which means I will have to make a lot of rounds to do that, I will not fail. So this is an adaptive attack that with verification and bomb testing, I can clone Wiesner's money. So you better not return it, or you better refresh it every time I ask whether a bill is good. So let's go to the second result, and the result is more general. Can I do it? Can I somehow defend against it? Meaning, can I choose a different list of states and so that this protocol doesn't work? Because this was really special. The QKD basis is very special because a C naught turns a 0 into a 1, keeps a plus, and minus goes into a minus minus. So this is really special. So what if I have just general states? So we can still do it, and the method that we produce is what we have named before a single copy tomography, meaning if I have a single copy of a state and I have some kind of a verification procedure whether we have that state, then I can find out whatever I want about that state. Well, meaning that I can calculate or measure the expectation values of what I want. So if I use a different list of states here besides the 0, 1, plus, minus, if I add, say, the y plus y minus as you suggested, or I add many more states, but states that are named, then it's not a problem for our procedure. Because, I'll tell you where the problem is, where we get completely unknown states. So what would I do for an unknown state? There's something, and I'm doing this C naught or whatever, but I don't know how far I am from that state, what I'm flipping. So I just guess a random axis and try to see how much the state is flipped about the axis. If I guess just right, like with a C naught on a 0, then it's flipped completely to an orthogonal state. So it's like the bomb case. What happens for the almost a bomb case? So it's an imperfect bomb that gets flipped a bit, but maybe not much. Well, it is flipped, and I can detect it. And why? Because this is my probe. It's rotated by a bit, and here's the bomb, or the system. Now I rotate it a little bit more, I open it up, and then I do the C naught, or the flip about some axis. And I either keep it, or keep it even when I look at it, or I look at it and I flip it. And there are these two small things. And when I didn't die, it means this is what I get, and that's a probe that's rotated by an angle that's maybe slightly bigger than this, but definitely smaller than that, because this part dying meant that the probe went back a little bit. And I claim that for a huge range of these angles, this behaves so that the probe actually converges to some angle that's small and it's fixed. So that means I kind of like rotate it and gets pushed back, not back to 0 exactly, but back to some stationary state. But there is a problem when there's a messy case that's like really, really almost no bomb. So that's something that gets flipped, but only very rarely. What happens then if we use our method is that it seems safe, we're looking, no, we don't look much with the probe, that how much do we look is noted by how much the probe is rotated. So first we don't look much, but nothing is happening, so we start looking more and more because the probe is rotated more and more. And then we actually start looking, and even though when we look we flip a little, it still is enough to kill us, because it will explode eventually. So this is a really messy case, and that's when the angle is something like 1 over square root of n, where n is the number of attempts that we're using, and the calculations are difficult and unexpected for me. We had to go to like third order in Taylor series. All right, so can we still do tomography with this strict testing? Even if the states are unknown, it can be in any direction that we want. Okay? Turns out that we can, because I'm standing here, and that's the third part of my talk. So here, how are we going to do it? We're going to make sure that every time we look at our system, we interact with it weakly. So no matter what we do not flip it much, even though I don't know what angle I'm flipping about or something. So we just need to be careful. I want a protocol that in every step that I do, every time I do something to the system, to my unknown qubit from a quantum bill, the probability of dying would be delta squared, where delta is some small number. So this is our protocol. We do a controlled rotation or a controlled anti-rotation, and it's going to be controlled on the value of some Pauli operator A. So say I want to do an expectation, calculate an expectation value for a Pauli, maybe Pauli X, Pauli Y, or Pauli whatever angle, on the qubit. So what I'll do, if there's a projection on the +1 eigenstate of A, then I rotate the probe one way, and if I get a projection on the other, I will rotate it that way. Okay, this together written is one unitary that we can do. What happens now? If it was just really like a +1 eigenstate of that, that means that I will be just rotating that way. If -1, I will be rotating that way. But if it's some interplay in between, I will be able to estimate that. So this is a unitary, and when you calculate something and you do it for small delta and go to second order, you'll find out that what happens is that the probe, if we didn't die, is actually approximately rotated by an angle that's proportional to this delta, but also proportional to the expectation value of the Pauli that we were looking at. And that means that by rotating this now n times, we get a unitary that's a rotation by some constant and the expectation value of A. And what can we do now? Well, we don't die, because the probability of dying is 1 over n, and we can choose n as large as we want. And the second thing, we can just do phase estimation of this unitary to find out what the angle actually is. And to do the phase estimation, we do it to some precision that we can calculate. And when we do this phase estimation for, say, x, y, z, or maybe adaptively for the results that we get as we're looking at them, as they're coming out, we will find out what the unknown qubit was. Because I know its expectation value x, y, and z, so I know what the qubit is. Then we need to do some calculations how precisely we need to do that. But still, altogether, this is an adaptive attack, which in another viewpoint can be named single copy tomography with a strict tester. So it's a tester that tells us, do we have the state? And if we don't have the state, we die. And still, we can calculate all the expectation values. So for example, if this was really a product of unknown qubits, we could copy it. So this, in conclusion, is the power of verification. If you have access to a verification box, even though the verification box never fails, because if it failed, you would die, you can still find out what the state is. And that's the conclusion. So I suggest that whenever you have a protocol with quantum money, you better make sure that the verification box doesn't give you any special powers, or reuse them after every time you verify something. Prepare or print new bills. Second thing, I gave you another application for the quantum Zeno effect that somehow goes away from the artificial quantum bomb thing, but it's about learning states that might be something useful, or you can give it as an exercise to your students in class. And then finally, I gave you another method for tomography with a box that gives you verification powers and never fails. Thank you.
About the strict testing,
Yep.
Do you have any ideas what happens in general if we have the non-strict testing? I mean, from what I understand, even the original Iriso-Weitman tester is kind of won't work with a bomb that explodes with some probability only, right? Is anything known there?
It works. It works. It was the one with where we got to a fixed point. If we know like the list of probabilities, or we kind of know which are the states, we can really test every one of them.
No, I mean the weak explosion where it
Yeah.
doesn't explode all the time.
We can still handle that. We
Also
can handle it. The one case that we cannot handle if the explosion is so weak, it's like very, very in a special range of weak. But if you tell me which one of like different, like it either is a bomb that's like 0%, 10%, 20%, 30%, then we can identify it.
Okay.
But if it's completely unknown, if it's continuous, then we are in trouble, and then we need to use the third method.
So this can be seen as a quantum version of an attack on one-time pad. When you use one-time pad many times, you can break it. So this is something similar, or?
So this is something that as if you did not use the one-time pad, but if you were just like verifying, like, is it still okay if there was some kind of deterioration, or possibly also if it was something that like I could send it to somebody, you could verify, if it was the same thing that we were moving over between us. But still, it seems like once you have just a copy, you cannot figure it out. But if you verify it many times, then you can. So I don't quite see the analogy with the one-time pad, but it's make sure you don't reuse. That's the warning. Just as with the one-time pad. With the one-time pad, it was clear. Here it was unclear. Now it is clear.
So if you don't reuse it, you are fine.
If you don't reuse it, you are fine. Like Molina, Potrus, and Thomas have proven that you're fine. And we have known that we're fine before.
Okay.
So I have a question. So I'm not very adventurous. So if you want to convince me to do this trying to forge game, I would like my killing probability to be exponentially small, right?
Okay, so it's not exponential. If it's exponentially small, you would have to need
an
exponential number of rounds.
Yes.
Yeah.
So what you say is that either you need to have a good probability of getting caught, or then the number of verifications that you need to do to the bank in order to copy basically is as large as your probability of dying. Right.
So we have to decide what's the cost, and then we send a peon to do it for us. And then some of them are expendable. So we make the estimates, and that's it, right? Yeah.
All I'm saying is that is the scheme still secure if you just allow a polynomial number of verifications to the bank?
No, with polynomial number of verifications, you get 1 over polynomial probability that you die.
I see. Okay, for me that's big enough.
Okay,
if
so
I die 1 over poly.
So we succeed with 1 minus epsilon, and the number of rounds is polynomial in the number of qubits and 1 over epsilon.